We will continue our treatment of quantum gases today. We haven't finalized yet the behavior of the fermions. Okay, so the subject is still quantum gases. And we're still treating fermions. Now, we have seen that the important quantity for fermions is the grand canonical partition function. And it goes as a sum over I e to the power minus beta ei minus mu I ni. We managed to separate everything into independent states, and the treatment of the grand canonical partition function as z1 multiplied by z2 multiplied by z3, etc., etc., etc. Okay. In our specific example, we had only 3 states. We managed to observe the probability occupation of any state. Occupation probability. And we've seen that this occupation probability behaves exactly the same for any state with energy epsilon. We'll write down it is as f of epsilon as a function of epsilon divided by mu. And this mu, which is the chemical potential, we set it as the Fermi level. Okay? And we've seen that exactly at 1, it crosses the line 1/2, the value 1/2, and depending on the value of the temperature, so for very low temperatures, goes as a step function from 1 to 0, and as the temperature becomes larger and larger and larger, we are getting more spreading of this probability. But it always have to go through 1/2 over here, okay, in general. And for extremely large temperatures, everything is going to be almost uniform. Now, it's important to remember that f of epsilon is an occupation probability. Epsilon is not the random variable over here, okay? So it's the indicator function. Is it occupied or not occupied? This is the random variable. Epsilon, or the value of the energy, is just a parameter. Therefore, we do not expect that the integral of this guy will give us 1. No station like that. Now, the last thing that we mentioned is, great, we can describe everything, and eventually we will describe quantum gas of non-interacting particles. Now, non-interacting it's misleading, I remind you. There are no energetic interactions, but there are always the Pauli exclusion principle that's present, and it makes extremely strong interaction. Okay, so we say that those particles are not interacting, but because they're fermions, the exclusion principle works. Effect is extremely strong. The problem, the main problem, is the applicability of this theory. In what sense? So if I take a chunk of metal. Okay, if I take a chunk of metal and I want to ask you something about the behavior in this chunk of metal, I want to compute the energy, I want to compute different properties of this chunk of metal. This prescription, okay, says that, well, I will have to assume that the number of electrons inside this chunk of metal is somehow distributed. Okay. It is varying as a function of time. It is true for any material. It is true for any material, but I don't really want to deal with number of electrons, which is modified as a function of time. Okay? I want to deal with a system where I can approximately fix the number of particles. Okay? I approximately can fix the number of particles and work with this fixed constant number. Now, if you look on the distribution, so let's say we have phi of n, and n is the number of particles, we know that in steady state, okay, in steady state, we're not going to have a modification. So in any steady state, if we have a number of particles which is not constant, there are going to be flux of particles in, some flux of particles out. They will cancel each other, and in general, what we expect is that the distribution of the number of particles inside the system will reach a steady state. Meaning, this distribution is not going to be a function of time. It's going to be something. Now, the regular assumption is, well, a lot of processes involved over here, so somehow we usually assume that this distribution is going to be maybe a Gaussian-like shape around its mean. Okay. And it will have something for small values and for large values. Now, if this n is very large, we don't care about this tail, okay, because of course n cannot be negative. Okay. Now, the problem, as I told you, is that I don't want to treat the number of particles as a function of time or something that can be modified. So therefore, we make the following assumption. When the assumption is, all right, we know that we have some sort of distribution. So let's assume that this distribution, because I have taken specific measures, I locked my chunk of metal in a controlled environment, and somehow the modification of the number of particles is extremely small. So I'm saying that this guy is small. How small? Let's assume that the variance, or the is going as 1 square root of n, when n is the average number of particles. So when I'm looking on a system with a large number of particles, I can assume that this distribution, or the width of this distribution, is extremely small compared to the the average number of particles. Therefore, the next assumption is, well, I'm going to use this formalism because it's actually treating the Pauli exclusion principle really nicely, but I'm going to switch to something different. And this something different, I'm going to assume that the number of particles, because I'm controlling the environment and because I'm assuming that this distribution is narrow compared to the number of particles, is a constant function. Okay. Now, this imposes a problem because everything that I developed was under the assumption that the number of particles is something. It's a random variable. Now I'm saying, well, the moment that we have this representation, we use it, and we stick inside this representation this constant number of particles. Okay? So, if you remember, we had several parameters that we could play with when we developed the grand canonical representation. The parameters were the temperature, which came from the specific average energy, okay, that we plugged inside the development of the formalism, and we also assumed that we have a specific, okay, chemical potential. So those were the two parameters that were responsible for the structure of this formalism. Now what I'm doing is I'm saying, well, no. Let's take some other parameter, a constant value, and stick it inside, which is going to be the number of particles. This means that I have to give up other parameters in my system. So initially we had temperature, which is beta, okay, and mu. Those were the parameters, control parameters. Everything else came out from the energetic structure and the parameters that I could control, temperature and mu. Now I'm saying we're switching, instead of T and mu, we're switching to some other parameters that are T, I want to control temperature, this is natural, and I also want to control the number of particles. Okay? So therefore, mu, which was responsible for all of this behavior, is not something that I'm just can't control, mu, in my perspective, is going to be a function of the temperature and the number of particles. It's not a free parameter anymore, okay? Because I want to control the number of particles inside the system. It has to be a parameter which is defined by the temperature and the number of particles. Okay? So therefore, I should have, or should devise a way to describe what exactly this mu is and how to find it. Remember, mu is important. Why is it important? It defines, at least for low temperatures, what is the Fermi level. So what is the energy up to which all my levels are going to be occupied and below which everything is going to be unoccupied. Moreover, we discussed this, that there are specific regions of the order of K Boltzmann T around the Fermi level. And all the dynamics and all the interesting stuff that happens, so anything that can define the behavior of my material occurs in this region of energies of the energetic spectrum, which is in the order of K Boltzmann T around the Fermi level. Right? So it's important to find what exactly is Fermi level. Now what I'm doing, well, beforehand, Fermi level was explicitly given to you by me. I'm saying mu equals to this and that. The moment I'm controlling the number of particles, mu is not something that I can give you. Mu is completely defined by, tell me what the temperature, tell me what the number of particles in the system, I will tell you what mu is. Right? Now, it's an important quantity, so we need to know, or we need to find this mu and describe it in terms of those two parameters, T and N. Okay. So this is what we're going to do now for two specific examples. One, it's a very simple toy model to describe how we find mu, and we'll see that it's indeed something that is dependent on the number of particles and the temperature. And another one is just a free electron gas. Okay, so the idea is, let's find mu. How to find mu. So what we do is the following. If we know our grand canonical potential, okay, we know that N equals to minus dou psi to d mu. Okay. So I know psi, I have its representation. Psi is minus 1 over beta log of z. I know z, it somehow depends on u, so I plug inside my partition function, I find my grand canonical potential. The moment that I have my grand canonical potential, I take a derivative of it with respect to mu, okay, plug a minus sign, and I have n. And then I take this equation, n minus d psi to d mu, okay, somehow, and afterwards I solve it. I find mu as a function of n and a function of t. So this equation, I use it as a definition and I solve it in order to find mu. Okay. So let's see two examples how it's done. So the first example is going to be the following. So my electronic structure, this is my T. My electronic structure is as follows. So I take energy epsilon 1, and I take another energy epsilon 2. Okay. Now, let's play with this and say the following. So I can have a degeneracy if it was just electrons with spin +1/2 and spin -1/2. I can say that epsilon 1 epsilon 1 can have particles with spin up and particles with spins down. Now, moreover, I would like to complicate it a little bit. Let's assume that I had another structure, okay, over here, another energetic level, okay, and basically this additional energetic level, okay, is somehow exactly the energy of this additional energetic level. Oh, you know what? Let's forget about it. This is all we have. Just epsilon 1 and epsilon 2, and that's it. The simplest case. Anyhow, it's going to be hard to calculate. Great. So let us write down, so what we know, it is the occupation, or Z, of epsilon 1 equals to, I'm sorry, Z equals 1 equals to 1 plus e to the power minus beta epsilon 1 minus mu, right? And Z epsilon 2 equals 1 plus e to the power minus beta epsilon 2 minus mu. Okay. No. Okay, so how we treat degeneracy? The question is how we treat degeneracy. We treat degeneracy, okay, in the following. We say, let's separate all the different levels. So this is the level with energy epsilon 1, and it admits only particles with spin up. So we have this one. Okay, and Z2 is the level with epsilon 2, which admits only particles also with spin up. Now we have two additional levels. Okay, let's call them Z epsilon 1, the level with energy equals to epsilon 1, and with spins that are pointing down. Okay, so this is going to be 1 plus e to the power minus beta epsilon 1 minus mu. It's independent of the spin. And Z epsilon 2, also with spin downs, is 1 plus e to the power minus beta epsilon 2 minus mu. Okay. So it's not multiplied by 2, it is a power of 2. Okay. So for this system, Z, it is Z epsilon 1 up, Z epsilon 1 down, Z epsilon 2 up, Z epsilon 2 down, which is Z epsilon 1 up to the power of 2, Z epsilon 2 up to the power of 2. You see the 2 is a degeneracy that is always present over here. Okay? Or in general, we can write it down as Z epsilon 1, Z epsilon 2 to the second power. Now, if I want to use this part, okay, I'm writing down as psi equals to minus 1 over beta log of Z epsilon 1, Z epsilon 2, I will put 2 over here. Okay. So the degeneracy is always coming over here. Let's assume that I will have electrons and they are not, they're having spins plus 1/2, plus 3/2, plus 5/2, etc., etc., etc. It's always this degeneracy will come up as a multiplicative factor for the potential. But for the partition function, is going to be a power. All right, so I can do this, right? Basically, take a derivative, etc., etc., or I can do the statistical representation. Remember, we did it yesterday. So the statistical representation, I will say, well, I want to compute the average number of particles. Well, either I take the derivative, as I told you, or I can say the following thing. An average, it is the average sum over I goes from 1 to 2 And here I have Ni. What is Ni? Ni is the number of particles that are occupying state or level number I. Because of the degeneracy, I'll have to introduce the possibility of having spin up and having spin down somewhere inside this. So where I'm putting here, over here, this is the degeneracy that's also present in this part. Why? Well, basically, I can say the following thing. Well, it is sum over I goes from 1 to 2, Ni up plus Ni down. Okay. If you want me to do this instead of saying, oh, I have a degeneracy, I have to write it down in this form, which is N. And I'm taking the average. It's the average of a sum. The average of the sum is always sums of the averages. So it is sum I of 1 to 2 N I up average plus N I down average. What is Ni? Up or down, it doesn't matter. Let's take up average. So the possibilities of Ni are either that it's occupied. So I have 1 multiplied by the probability that it's occupied, Fi, plus it is not unoccupied, which is then Ni equals 0, multiplied by the probability that it's not occupied, which is 1 minus Fi. Fi, I know what it is. It is simply 1 over e to the power beta epsilon I minus mu plus 1 multiplied by 1. That's it. So you see, it's independent of the spin up or spin down. This is why Ni up equals to Ni down. This is why I can put just the degeneracy prefactor 2 over here. Okay. So in total, I'm taking the following form. Average N equals 2. So we have EI equals E1. So it is 2 divided by e to the power beta epsilon 1 minus mu plus 1 plus 2 divided by epsilon beta epsilon 2 minus mu plus 2 plus 1, I'm sorry. Okay. So you see, in this equation, we have a dependence of n, which is not a control parameter. Okay. It depends on the values of the energetic structure, epsilon and epsilon 2, but this is something that we do not modify and do not control, so it's just there in our system. But we can control beta, which is the temperature, and we can control mu. Now we switch places and we say, well, this is not n, okay, an uncontrolled. This is a controlled parameter. Okay. This is n. And this n is equals to 2 divided by epsilon beta epsilon 1 minus plus 1 plus 2 divided e to the power beta epsilon 2 minus plus 1. And here we plug something that we now wish to find and we are not controlling. This mu now is going to be a function of n and beta. Epsilon 1 and epsilon 2 we do not control, they are just something a part of our question. Okay. So the solution of this guy, and this is something that we can use in order to define what is our mu. Now notice, in this perspective, mu is not just a function of n. Mu is a function of n and temperature, which is beta. Okay. How you usually solve it? Well, hard, and usually you can't, even in this very specific limit. But we can find the Fermi, at least at the limit when t goes to 0. Okay? This is not a nice equation. You cannot just simply solve it. But maybe you can at this specific limit when the temperature goes to 0. Okay. So what you do in this limit when temperature goes to 0, so you have this expression e to the power beta epsilon minus mu plus 1. Plus 1 is not interesting, so the only thing that we look on is just e to the power beta epsilon minus mu. Now, this is epsilon 2, this is epsilon 1. The expectation is that in the very low temperature, what is going to happen? So what's going to happen is that at extremely low temperatures, all the lowest states are going to be occupied, we know that, okay? And all the upper states are not going to be occupied. So if we plug, if we say the following thing, let's assume that we have only 2 particles. If you have just 2 particles, so for example with n equals to 2, at a very low temperature level, those 2 particles will manage to occupy the lowest level, okay, at extremely low temperature. Now, if they're occupying the lowest level, the Fermi level have to be a little bit, or at least, or at epsilon equals epsilon 1, or above epsilon 1. Because if we put the Fermi level below epsilon 1, if we put it somewhere over here, this means that epsilon 1 we cannot occupy epsilon 1. Remember, the idea is we occupy everything and the temperature goes to 0 limit. We occupy everything, all the levels, up to the Fermi level, or we do not occupy anything that's above Fermi level. So if we assume that we have just 2 particles, okay, we know that the Fermi level has to be somewhere above epsilon 1. Okay. Now, it cannot reach epsilon 2. Why? Because we know that if we have only 2 particles, okay, if the Fermi level is at epsilon 2 or a little bit above epsilon 2, also the second level is going to be occupied. But it cannot be occupied because we set the number of particles to be 2. If we set the number of particles to be 3, it's something else. But we set the number of particles to be 2, so we know that mu is somewhere over here, in between. Okay, so this helps us. Yes?
אפשר להגיד שכאילו פרמי לבל כן נמצאת מעל אפסילון 2, אבל פשוט מספיק חלקיקים, כי הגדרת יש רק 2 חלקיקים. Because the
so you're saying the following. Put it over here. Put it over here, right? And you just say, well, you just have 2 particles. Okay, you just have 2 particles, and for those 2 particles, well, they're just sitting over here. There are not enough particles to sit in the epsilon 2 level. You break the formalism. Remember how we derived all of this? We said the following: n is undefined, right? N is undefined. Therefore, n can be anything. And the result that we obtain, that in the t goes to 0 limit, okay, t goes to 0 limit, all the energies are occupied up to the Fermi level. Now, I know that what I'm doing here is just reversing the order. I'm saying, well, let's forget about the constant mu, let's take n to be constant, but you cannot switch them simply, okay? Because you have this constraint. And the constraint says everything up to the Fermi level have to be occupied. So you cannot define the number of particles to be 2 and say, well, this is below the Fermi level, but it's still not occupied. You're breaking the constraint. Remember, this is a harsh constraint. We can switch, we can use this guy, we can say, oh, this is n. But you cannot plug over here something that won't satisfy the constraint that at the t goes to 0 limit, everything below the Fermi level is occupied. Okay?
אבל גם אם כן הייתי משהו לי פה 1 ו-1, זה גם היה שובר, כי אכלוס מלא הוא...
So it will define, so exactly. The choice of n, well, we're doing this mathematical trick, but you're constraining what n's you can choose. That's what I'm saying. If we have extremely large system with many levels, usually it's, well, you have a lot of levels and you don't care about this, okay? But when you're looking on the system with only 2 levels, it's not any n that you can choose. That's it. That's the answer. Remember, we started with everything which was very self-contained and mathematically justified. When you switch the roles, okay, you cannot choose specific values of n such that specific constraints are not going to be satisfied. You limit it. Okay? Yes?
But you also can't choose such a small n because your derivation was that n is very big. So
where it was very big. So the assumption that in this example, I'm just saying, let's use this. What I'm saying is when it's justified. When n is very big, all those constraints are unimportant. Okay? But I can still do this mathematical treatment even with small n's.
But in small n is so n will
So for small n's, this mathematical trick is fishy. I agree with you. It is fishy. It's not fishy when n is extremely large and you have very narrow distribution, etc. It is fishy here, and this is why I have those questions. Well, why you cannot do this and that? Well, because you already see the constraints. Okay. Yes. Okay, so in the limit when t goes to 0, what we know is that all the energies below the Fermi level have to be occupied. Okay, this is a strict constraint that we obtain from our formalism. Now, if I'm saying to you, let's use this and say that we have only 2 particles. Okay, so when I'm looking on this equation, so provide me mu, provide me temperature, and I will tell you what is the average number of the particles is. I'm switching the roles, and I'm saying, well, let's say that I have n equals to 2. Okay? When n equals to 2, and I'm taking t goes to 0, I have to satisfy the constraint that all the levels below the Fermi level are full. Okay? So if I have 2 particles, everybody have to sit over here. It has to be full. What is full? It can contain only 2 particles. One is spin plus 1/2, one is spin minus 1/2. Okay. Yes, if I will take n equals to 3 or something. No. Everything have to be full. I cannot have part of the particles over here and part of the particles over there in the t goes to 0 limit. It can be the situation when t is large enough, but for extremely small t, it is not. Okay? And only in this limit I can somehow do with this simple example. Exactly. So if you're thinking about the occupation probability, okay, F epsilon, and here I have epsilon divided by mu, I know that in the low temperature limit, it's a step function. This and this. Okay? This is in the t equals to 0 limit. Okay? So I cannot have some particles over here while there are some particles not present over there. The probability to find the particle in this specific level is 1. And here it's 0. It has to be like that. I cannot, so this step function, this is the crucial constraint. Ilutz. I simply cannot break it. I can do a lot of mathematical exchanges, etc., but this has to be satisfied. Okay? This is the physical constraint. Great. So let's look on this guy. Okay? And the important thing is epsilon minus mu divided by k Boltzmann t. Now, this guy, because t is going to 0, it had only two limits. What are the different limits when t goes to 0? And those two limits depends on whether epsilon is larger than mu or epsilon is smaller than mu. Okay? So when epsilon minus mu is smaller than 0, okay, this guy goes to minus infinity, right? Okay. When epsilon minus mu is larger than 0, okay, k Boltzmann divided by k Boltzmann t, so this is epsilon minus mu larger than 0, this guy goes to plus infinity. Okay. So I'm using this, I'm saying the following thing. We have 1 over e to the power beta epsilon minus mu plus 1. Okay? And I'm taking the t to 0 limit. Okay. Now, there are two options. When epsilon minus mu is smaller than 0, okay, all of this is going to minus infinity. So epsilon to the power of minus infinity, it is 0, right? So I have a big term and I have a small term. So you can say, well, it's just 1, but I don't want to lose the connection to epsilon, okay? I'm saying that it's 1 plus something, right? So what is the Taylor expansion of 1 plus something? If I have 1 over 1 plus x, and x is small, it goes to
1 minus x.
1 minus x. Okay? So this guy, in the limit when t goes to 0, and epsilon minus mu is smaller than 1, so if you plug it over here, epsilon 1, and I know that mu is somewhere here in between, now that this guy will go to 1 minus e to the power beta epsilon 1 minus mu. Okay. Now, the other limit, when we have e to the power beta epsilon 2 minus mu plus 1, in the t goes to 0 limit, what we have, so we know epsilon 2 minus mu is larger than 0, because we assume that epsilon mu is somewhere over here. So epsilon 2 minus mu is larger than 0. So we're looking on this limit. So epsilon minus u divided by k Boltzmann t goes to infinity. E to some extremely large power, it's extremely large number. So I don't care about this one. Okay? So what I'm getting is that this guy is just e to the power minus beta epsilon 2 minus mu. Okay? Now I'm coming back to this equation. So what happens over here? We assume that n equals 2, so it is 2 divided by, equals to 2 e to the power beta epsilon 1 minus mu plus 1 plus 2 divided by e to the power beta epsilon 2 minus mu plus 1. Right? So I don't care about this 2's anymore. So I have 1 equals to 1 over e to the power beta epsilon 1 minus mu plus 1 divided by a to the power beta epsilon 2 minus mu plus 1. And now I'm taking the t to 0 limit. So 1 stays 1. Okay. Over here, it is what? So this is the guy. It is 1 minus e to the power minus beta epsilon 1 minus mu. Okay. This part. Plus without minus, right? Without the minus. I don't have the minus over here. This guy goes to e to the minus beta epsilon 2 minus mu. Okay. Now 1 and 1 cancels out, and we have e to the beta epsilon 1 minus mu equals to e to the minus beta epsilon 2 minus mu. Okay, let's take the log of two parts. So therefore, beta epsilon 1 minus mu equals to beta or minus beta epsilon 2 minus mu. Beta and beta cancels out, right? So we have epsilon 1 plus epsilon 2 divided by 2 equals 2 mu. So what we see that when we have only two particles in the system, the Fermi level at the T goes to 0 temperature, sitting exactly between those two. This is a simple example. The moment that we will include some additional structure, the result is going to be modified. Okay? But you see, it's actually hard to solve those problems because of the presence of linear dependence on n and exponential dependence on mu. Okay? And there are a lot of different prefactors. So it's hard to solve only if the t goes to 0 limit, when we always make some assumptions due to the constraints about the number of particles that are present in the system, and we take those approximations saying, well, you're above the level, you're below the level, only for this you can solve it somehow. Exactly. Well, the result is right, or self-satisfied, or self-contained. I assume that mu somewhere over here, and this is exactly what I've got. Okay. Great. Now let's see how we do it for a slightly different example of free electron gas. But the idea is going to be exactly the same. You take a system, you use the grand canonical representation, you derive the dependence of n on something, and from this expression you solve it and you find mu. Great. It is going to be dependent on n. It is. And it's actually going to be, for large n, it's going to show us a very interesting result. This is the whole point, that the Fermi level depends on the number of particles that you have inside your system. Yes? Because we plug inside the number of particles. What will the number of particles supposed to do? So I'll plug something else. Let's assume I'll plug something else here. It's going to be dependent on it. Okay. So free electron gas. Electron gas. Let's assume that I put particles inside the box, which is L by L by L. So L to the third power equals to the volume of the box. Okay. And I assume that all those electrons, so this is my metal, right? And so all those electrons inside, they do not feel each other. Basically, I'm saying, well, they have kinetic energy. There's some energetic spectrum, okay? But they don't care about each other at all. Okay. In what sense? In the sense that they do not interact, and the only interaction is the Pauli exclusion principle. So the free here is a little bit misleading, but we're used to it with the electrons already. Okay, so what we know that there's going to be some electronic structure, or not electronic structure, energetic structure. Okay. And this energetic structure is actually going to be continuous. Right? It's not explicitly discrete levels, but those levels are very, very, very narrowly displaced. Great. So we are going to use the continuum limit. We're going to use the continuum limit, while the grand canonical representation is going to be exactly the same. So z, the grand canonical function, is going to be a multiplication of all the different energetic levels of z epsilon, and all of this is going to be to the power of 2. The power of 2 is because each of those tiny levels can occupy particles with spin up and particles with spin down, and we can treat them as if they are different energetic levels. So therefore, we will have the power of 2 due to the degeneracy. Great. So, if we would like to compute something, for example, psi, which is -1 over beta log of z, we know that it is what? -1 over beta log of this multiplication over all the possible epsilons, z epsilon to the power of 2, which is -1 over beta. We will have 2 over here, and log of a multiplication is a summation of logs. I sum over all the possible energies that I have inside my system. Okay? And here I have log of z epsilon. Now, z epsilon, because the only thing that I have inside are particles that are not interacting, okay? I'm looking on the different levels and I'm saying, well, z epsilon, it is e to the power minus beta epsilon minus mu plus 1. It's exactly the same structure as we had before. So everything is known. Everything is known inside. So I plug this z epsilon inside the log, and I'm going to have -2 divided by beta log, or I'm sorry, a sum over epsilon log of 1 plus e to the power minus beta epsilon minus mu. Problem is, what is the different epsilons that I have inside? So what do we say? I will plot it. If I'm assuming that all the different energetic structures are extremely close to each other, so I'm taking this summation, saying, well, we can do a representation by means of the integral, right? I don't want to sum over all the different levels. I'm going to integrate over all the different levels. So psi equals to -1, or I'm sorry, -2 divided by beta, and I have a sum, and it will start from 0 and it will end up at infinity. Okay, and here I'm going to have a log of 1 plus e to the power minus beta epsilon minus mu. Now, and I have the epsilon over here. Is it enough?
No, you need the density of states.
I need the density of states.
Why are you stuffing it to infinity and not some h bar omega divide?
It's electrons. So omega d pi came from the idea that I have some specific number of degrees of freedom. Is there any limitation on the possible energy that those particles are going to have inside my box?
Well, maybe I need to diagonalize the Hamiltonian.
Hamiltonian is very simple. Pauli exclusion principle applied, and there are 3 particles with only kinetic energy.
Okay.
Okay? Well, the moment that we are saying there are only particles with kinetic energy inside, the energies are from 0 to infinity. In principle. We'll see, maybe it can be modified. But anyhow, because I'm not counting those states, I'm integrating over them, I have to have some d epsilon over here. The question is, what is this d epsilon? Okay, so what do we know about those electrons? They're free particles, but they're not exactly particles, right? They're quantum stuff. So they are also waves. Okay, so they are waves, and I'm saying those particles cannot escape this box. They have kinetic energy, but they are limited to this box. So I know that the wave vector, or the wave function, has to obtain the values of zeros at the boundaries. Okay? So basically, those are standing waves inside the box. Okay? So if I know the k vector, the density of states, if I'm knowing that, well, let's use the wave vector k, okay? And I know what is this k is, I know because we did it for the Debye model, and who cares? Real waves, some other waves, is the same idea. Boundary conditions for standing waves are the same for real waves, or the waves that we imply for the wave function of quantum mechanics. We know that this d E equals to v squared divided by 2 pi d 2 pi squared d to dk. Oh, I'm sorry. Let's say the number of states. Number of states. K to the third, here we had 6. Okay. Do you remember this result from the Debye model? So we used exactly the same formalism. We had standing waves inside the box, etc., etc., etc. We assumed that there are only standing waves. Basically, it's saying, well, the amplitude of the wave here is 0, and the amplitude of the wave over here is 0. Is exactly what we would do for the wave function in quantum mechanics. So we'll get exactly the same result if I'm using k description. Okay. D of epsilon, it is d to d epsilon. Okay. D to d epsilon of the number of states. So d epsilon equals to, when we take the d to d epsilon of v by 6 pi squared k to the third equals to v divided by 2 pi squared k squared dk to d epsilon. But I know the following thing. Epsilon, the energy, p squared divided by 2m. Right? What is p? H bar k bar. H bar squared, k squared divided by 2m. Okay. So I have this connection of epsilon equals to h bar squared, k squared by 2m, or k equals to 2m epsilon divided by h bar squared. So you see, I have the description of the density of states. It depends on how k varies with epsilon, and I know this because I'm assuming that it's a free electron gas. Okay. So from this guy, I know that dk to d epsilon equals to 1/2 a square root of 2m h bar epsilon. So let's plug everything inside our expression of the position of the particle, right? So we're treating particles inside the box. So there is a wave function that describes their position. Okay? The probability to find the particle in a specific point is going to be wave function squared, right? But the wave function is waves, and it has specific boundary conditions. I treat them exactly as I treat waves. This is actually how Schrödinger got them. He thought about waves. And this is why quantization comes into quantum mechanics, right? Because of the boundary conditions. Next step. Yes.
H bar bar.
H bar squared. Yes. Thank you. Okay. So we plug everything inside, and we have d of epsilon equals to v 2 pi squared. K squared, it is 2m epsilon divided by h bar squared, right? Multiplied by s1/2 a square root of 2m h bar squared epsilon. Okay, so let's make it a little bit nicer. Well, actually, don't count. 2 divided by 4 pi squared, and here we have 2m divided by h bar squared to the power 3/2, and here we have epsilon to the power 1/2. Okay. So eventually, our grand canonical potential psi equals to minus 2 divided by beta, an integral from 0 to infinity, a log of 1 plus e to the power minus beta epsilon minus mu. And here we have v 4 pi squared 2m h bar squared 3/2 epsilon half d epsilon. Hooray! We know the grand canonical potential. Everything is nice. The thing is, remember, our goal somewhere over here is going to be what is mu. Right? Because this is a very important quantity. Now, how we solve it? Oh, we can go backwards and solve in the statistical way, but the moment that we have the grand canonical potential, we don't have to. So there are always two ways. Either you use the statistical definition of what is the average number of particles, or you use this thermodynamical relation, which is n equals to minus d psi to d mu. So we have to take some derivatives somehow, etc., etc., etc. Okay, so how we're going to do it? Let's take the derivative. So minus and minus, they're killing each other. So n equals to, let's write it down. So minus d to d mu of whatever we have inside, which is minus 2 divided by beta, an integral from 0 to infinity, log of 1 plus e to the power minus beta epsilon minus mu, v 4 pi squared 2m h bar squared to 3/2 epsilon to the 1/2 d epsilon. Great. The only thing that matters is this term over here. And I'm assuming that the integral is converging uniformly, therefore I can plug this derivative inside the integral because the derivative with respect to mu and the integral with respect to something else. So I have n equals to, now let's take everything that is not related to the integral outside. So we have over here v divided by 2 pi squared we have K Boltzmann T over here, or let's write it with beta. Beta, we have 2m h bar squared, 3/2. Okay. Inside we have an integral from 0 to infinity, epsilon to the power 1/2. Here we have d to d mu of log of 1 plus e to the power minus beta epsilon minus mu d epsilon. Great. The derivative of the logarithm is fairly easy. Okay, so let's concentrate only on this guy. An integral from 0 to infinity, epsilon to 1/2. Here we have a derivative with respect to mu, which is 1 over 1 plus e to the power minus beta epsilon minus mu, okay, multiplied by beta, right, e to the power minus beta epsilon minus mu d epsilon. Okay. So we're looking on the integral of 0 to infinity of epsilon 1/2 e, let's take beta out, so we have beta. Now we can push this epsilon minus beta epsilon minus u downwards, so we have e to the power beta epsilon minus mu plus 1 d epsilon. Okay, so this is still a nasty integral. If you call all of this A, right? So we know that the number of particles, which we forget now that this is the average, okay, this is the average, this is the specific fixed number of particles which you use. The average number of particles, which is n, it's not average, equals to this A, okay, multiplied by beta, multiplied by this 0 to infinity, epsilon to the 1/2, e to the power beta, epsilon minus mu, plus 1. Okay? And somehow we need to solve it. Now, as in the previous example, well, it's going to be a nightmare to solve it, and then afterwards you will get some complex function, a crazy function, and then you have to solve this crazy function in order to find the mu as a function of temperature and n. It's tough, okay? Or in general, not really impossible. You can do it numerically always, right? Now, for fermions, the situation becomes nice, really nice, the moment that you say, well, I'm assuming that I'm going to work in the low temperature limit. Okay? Why? Because you know something about the system in the low temperature limit. As in the previous example, right? So what I've done, I said, oh, in the low temperature limit, the lowest levels are going to be packed, fully packed, and above the Fermi level, there's going to be nothing. Okay? All right. So what do I know in the t goes to 0 limit? I know something, that occupation fraction, remember this f of epsilon, as a function of epsilon divided by mu, goes to this step function. Right? This is 1. This is 1. Okay. This constraint I have to satisfy all the time. Now, look on this guy over here. What do I have? What is this specific part? What is this? This is exactly f of epsilon. This is the occupation fraction. or it's also called the Fermi distribution. Okay? So I know that this part over here is a step function. In the low temperature limit, whatever is standing over here, we can write 1. This is f epsilon. So I don't need to solve this integral. I know, well, I have a step function. The step function is in integral. It's always easy to solve, right? It basically modifies the limits of the integral. That's it. So in the t goes to 0 limit, okay, this nice integral, or not so nice, is transformed into an integral from 0 to mu Fermi, okay, from 0 to mu Fermi of epsilon 1/2 d epsilon. And that's it. All the levels up to mu Fermi are occupied. Anything above mu Fermi is not occupied, and that's it for me. Great. Yes?
לא הבנתי להם איך זיהית את זה כהסיכוי להיות ברמה נגדית מסוימת.
Do you remember the example when I have a specific levels? This is epsilon 1, and this is epsilon 2, and this is epsilon 3. And I said, I proved that the occupation fraction, which is the probability to occupy level with some epsilon, it is 1 over 1 plus e to the power beta epsilon minus mu. I have shown this. I'm looking on this guy. Mathematically, is this function the same as that function?
Yes.
So if this function is the same as that function, I know that in the t goes to 0 limit, it is a theta function. And that's it.
כן, אבל כאילו, לא מסתדר לי פשוט האינטגרל עצמו, כי כאילו אתה עושה אינטגרל פה על האנרגיה, כאילו שורש האנרגיה כפול הסיכוי להיות באנרגיה הזאת. אז כאילו, איך, כאילו,
So the problem is, well, that I have epsilon to the power 1/2?
כן. וגם בכללי, למה יש עכשיו אפסילון, כאילו, אם זה רק, כאילו, אמור להיות שאני אין.
So look on this guy. Look on this guy. Do you agree with me? It's a bit of mathematical thing, but what I'm saying is as follows. I have an integral from 0 to infinity of epsilon to 1/2, and here I have some function, let's call it g of epsilon, d epsilon, okay? I'm just looking on this guy over here. This g epsilon, it somehow also depends on t, right? Now, I need to calculate this general integral in the limit when t goes to 0. Okay? This is the mathematical question. All right. Here, I'm doing whatever physicists are usually doing when they see an integral like that, and mathematics shout at us, it's impossible, you never do this, saying, let's take this limit inside the integral. So this guy, a physicist approach, is, well, this is an integral from 0 to infinity, epsilon 1/2, limit t goes to 0 of gt of epsilon. Can I do that as a physicist, not as a mathematician? I can do that. Now I know that this limit of this guy, let's now take the limit before we take the integration. We take this limit. I know that in this limit, this is a step function. Okay? This is a step function. So it is a theta, so limit of t goes to 0 of gt of epsilon. It is theta function of epsilon. It cannot go below 0. And it's a theta function of 1 minus epsilon divided by mu. Is this a limit? I plug it inside. I have an integral from 0 to infinity of epsilon to 1/2, theta of epsilon, theta of 1 minus epsilon divided by mu, d epsilon. Kosher? Great. Now, the next step is, whatever you always do with the theta function inside the integrals, you just get rid of them and you look on the limits of your integration. So this guy go to 0. So this is fine. Okay? This theta function simply says to us, well, you cannot have negative epsilons, but we haven't them in the first place, so we don't care. This guy.
That we cannot have greater epsilon than mu.
Exactly. Yes. So this modifies the upper limit of the integral. Okay. So what we have is the integral from 0 to mu of epsilon to 1/2 the epsilon. Fine now? Yes.
We started by saying we want to calculate the dependency of mu as a function of n and t, and we keep taking the limit of t to 0.
Because I cannot solve this for any general t. So what I have to do for a general t, I will say, yes, this is a theta function. But in reality, it's not exactly a theta function. It's something like this. Okay? And now, I should have done, what I should have done is to say, let's assume that it's a theta function, and there are some corrections to this theta function. What are the corrections? Well, there are some corrections in this specific region. And I can introduce those corrections to the limit. Okay, so the limit is whatever I'm getting those theta functions plus something. Okay, and I should introduce them into the integral. Okay, and solve it. It's a cumbersome solution, it's long, but it's doable. Right? It does not serve our purpose. Okay? Because there is a point that I would like to make at the end of this calculation. Anyhow, this integral, it is what it is. What is the solution to this integral? No, what do you say? 2/3 mu Fermi to the power 3/2. Yes, this is the solution. The problem is that I erased whatever A is, right? We have this A, and I don't remember what A is, so you have to tell me what A is. Wait a second. So let's write it down. So N equals to A beta, and the solution of all this integral is mu Fermi. Mu, I'm just not saying just any mu, it's just mu Fermi for us. 3/2. What is A? It's V divided by 2 pi squared. Beta in the denominator. Beta, and here I have 2m h bar squared 3/2.
Yes.
Great.
You forgot to add the 2/3 from the integral.
Oh, yes, great. Thanks. 2/3. Okay, so now we have n equals to beta and beta cancels each other, so we have v divided by 2 pi squared.
2 and the 2 cancel each other.
2 and 2 cancel each other, so we have 3 pi squared. 2m h bar squared 3/2 mu Fermi to the power 3/2. Right? So mu Fermi. Right? So this is where the up to which level all the electrons are sitting. It is, so we have n divided by v to the power of 2/3. Okay. And also we have over here 3 pi squared. We put it here, 3 pi squared to the power of 2/3, and here we have h bar squared divided by 2m. Okay. This is the mu Fermi, and the t goes to 0 limit. Okay, so, well, it's not a problem. It's a problem?
It's a problem because because when we research gas in the lab, T isn't really that close to zero.
All right, okay. I'm hearing you, and I'll discuss it in a second, okay? So we know how to see this limit of t goes to 0. We can add this corrections to the theta function. We can do that mathematically. But I don't need it, okay? Why? Well, what is this guy, okay? What is this guy when plug everything inside? So, if I plug, let's take this volume, and we take something like, what is the density? So, N divided by V, for a metal, it's on the order of 10 to the power 22 up to 10 to the power 23. Okay, so this is the density of electrons inside a regular metal. We're assuming that we have 1 electron per ion, and the density between the ions, or the distance between the ions, is of the order of 5 angstrom, something like that. So this is the number that you get. Okay. Now, the moment that you plug everything inside, and there is a big number, which is N divided by V, okay, what you'll get is that mu f, and I would like to describe it in terms of temperature, so I will say it is some K Boltzmann by some T effective. This have the scales of the temperature of the energy, okay? I'm saying that mu f divided by K Boltzmann, so when I plug all inside, I plug the N divided by V, on this scale, I plug h bar, the mass of the electron, everything, I divide it by K Boltzmann. What I'm getting is 10 to the 4 or up to 10 to the 5 Kelvin. What this means, okay?
That respectively to the density of the ions, the temperature is negligible.
Exactly. So I'll explain it to the crowd. So mu f, the Fermi level, is the following thing. In the t goes to 0, okay? In the t goes to 0 limit, we have our spectrum of energies starting from 0 and going up. Okay? We'll go up. Okay? Now, we know that all the lowest levels up to some specific mu Fermi in the t goes to 0 limit, okay, are full. So we have a lot of particles sitting on top of each other over here. Now, because we have a huge number of particles, right? We have a big number of particles, this mu Fermi level is going to be high. Okay? So this is what we've got. Okay? The Fermi level for a realistic system with a lot of particles have extremely high value. Okay? Now, well, that's fine, but who cares? You can say it have a high value and they all piled up on top of each other. But it's not only that. Let's assume that we now, and I will do it with waving my hands, let's assume that we are not exactly at the t equals 0 level, but at some specific temperature which is a little bit above 0, okay? We're still going to be in some vicinity of mu Fermi. Okay, so let's say that we are working not at exactly 0, but we're working at some vicinity, 20 Kelvin, 100 Kelvin, 30 Kelvin, 300 Kelvin. It's still negligible with respect to 10 to the 5 or 10 to the 4, right? So even if we are working in the room temperature, okay, the modifications around mu Fermi are going to be negligible with respect to this extremely huge value, right? So this is point number one. Even we increase our temperature, okay, we increase it, not extremely, okay, so we're not going to this very high temperature, but we're working around to room temperatures or below. The modifications due to those additional, temperature is negligible with respect to the mu Fermi. Okay, maybe we'll push it a little bit up, but it's still extremely large value. Okay, and this is point number two. Let's assume that, well, here we had absolutely no interactions between the particles. All the particles were completely free. The only limitations, two limitations, particles inside the box and Pauli exclusion principle. The box entered just because, well, we had this volume over here. The Pauli exclusion principle, this is what caused all the electrons to sit one on top of each other. Let's assume that I'll do this a little bit more realistic. In a sense, I'll include interactions between the electrons, okay? Because electrons have interactions between them. Okay? What is the value of those interactions? Are they going to be comparable to my kinetic energy? The answer is no. Why? Do you remember what I said to you? That the only particles that are participating in the game, okay, are particles or are levels, energetic levels, that are sitting in the vicinity of mu Fermi. Okay? Now, mu Fermi is extremely large, and this is just the kinetic energy. It has a K Boltzmann T effective on the order of 10 to the 5 Kelvin. Let's assume that I introduce interactions between those guys. The kinetic energy is much higher. The effective kinetic energy of those guys who are sitting over here is much higher than the potential energy that comes due to the interactions. Therefore, I can simply kick out of the system my potential energy. I don't care about it. Okay? So when I have interactions, when they are not extremely large or extremely important, I have some interactions, regular interactions. Due to this extremely high volume mu Fermi, they are negligible. Okay. So this is, even so I worked in the t goes to 0 limit, I can say something very important about the system. And that is that due to the large size of mu Fermi, I don't care about interactions. Okay, and I know what my effective energy of my different electrons is. Okay. Even if I increase it, I will heat it up. The description still works pretty well. Okay.
Well, if you say that you can address interaction, say there's no collisions because the mu Fermi is so high, why don't we simply address this state as an ideal gas?
It's not ideal gas. There is exclusion principle. The exclusion principle is extremely important. The only thing, and this is the only thing that causes all of the effect over here, is that we have Pauli exclusion principle. If you have ideal gas, well, they can sit whatever they like on this electronic spectrum, right? Energetic spectrum. It's only due to the Pauli principle they pile up. So there is no interactions, but there is. Okay? And this is very important. This is why the quantum system is so different than the classical system. In the classical system, you don't have this piling up of the electrons. It's not a cumulative effect. It's the effect of everybody, and everybody do whatever they like. Here, they have to fill up all the different states, and they're sitting up there. And all those electrons that are somewhere up above, they're doing something, but they have extremely large energy. So, who cares about some additional potential energy in the system?
אתה אומר שבגלל שהאנרגיה הקינטית ממש גבוהה, זה תמיד מהדה, אבל הנמוכים הם לא באמת.
But, right. What I'm saying is not that the particle that it's sitting over here is not going to move. I'm saying, no matter when you're looking on the system, this state is always occupied. And this state is always occupied. And this state is always occupied. So the only particles that are precipitating sitting over here, right? So some states are occupied, some states are unoccupied. So particles are moving from occupied states to unoccupied states and vice versa. The energies of those states is very, very large. So this is their energies. That's it. Those states with low energy, always occupied. they're always occupied. Nobody comes or goes over from there. That's it. Okay, so this is the story, and the quantum effect is extremely, extremely, extremely important. We'll finish here, and what we'll do, well, next week, no classes, all right? I'm in a conference, but what we'll do after next week is describe what happens. So this is the story of fermions. What happens for bosons. And for bosons, the story is even more interesting. Okay? Very nice effects for bosons. We'll see it later. I remind you that in order for me not to schedule the additional lectures on Wednesday, 8 a.m., you have to provide me some specific dates. Okay? A reminder to you all. So, Oz, can you take care of it?
Yes, no problem.
Okay. Thank you. כן.
מה קורה כשהטמפרטורה עולה מעל
אתה צריך ללכת זה נשבר. ואז יש לך דברים כמו פלזמה ועוד שטויות. אבל צריך לקחת את הסכין, אתה צריך ממש ללכת לטמפרטורה. או, תשים לב, זה מגיע מהדבר הזה, שהאוויר